Chapter 3, Atoms and Ionic Bonds. Here are the suggested chapter problems from the end of the chapter, and here we go. So when we talk about bonds, we're talking about what's going on with the electrons, what's attracting these atoms to each other. We have two different major types of bonds that we're going to talk about in this chapter, covalent bonds and ionic bonds. Covalent bonds share electrons, and they are known as molecules. Ionic bonds transfer electrons, so we form ions, and they're called formula units. So, a chemical bond that's formed through sharing electrons. The simplest unit is called a molecule. A lot of people mess this part up with the namings. So, if you're dealing with a covalent compound and they determine a molecule, if you're dealing mostly where people mess up the terminology is with ionic compounds, they can refer to them as molecules. And we kind of just let that slide, but I'm going to be very specific. So some elements actually exist as molecules rather than individual atoms naturally. Those are the Brinkelhoff that we talked about. These are our 7 diatomics. You need to know those and make sure that you know that we could also do horses need oats for clear brown eyes and have no fear of ice cold beer. Whatever it is that have you remember it. There are 7 naturally occurring diatomic molecules. Those are not the only elements that exist in a multivalent form. We also have sulfur and selenium, which appear as S8 and Se8, phosphorus is P4, and so on. But these ones you need to know. It's extremely important when you go to write the formulae for these into an equation that you write it correctly. So when using these in a chemical equation, you must use them in the diatomic form. So covalent bonds are generally formed between 2 or more nonmetals and a metalloid and a nonmetal. Sometimes for this class, for naming purposes, we're going to go with it, but these are generally. There's always exceptions, right? And we can actually represent these through what are called ball and stick models as well as space filling models, and we're going to actually use what are called Lewis dot structures later on. These are models. These are ball and stick models, and these are space filling models here. You can see that the ball and stick models are a lot easier to read, but it doesn't show necessarily the space that is taken up. So this is just going to be something you'll see as you go through your textbook. Now, covalent bonding, the atoms are going to be sharing the electrons to form the bonds. So this would be hydrogen. One hydrogen has this red electron, one hydrogen has a blue electron, and they share this so that this hydrogen, gets to count like it has 2 electrons, and that's happy for this hydrogen, right? He likes to have only 2 electrons because he only has one s orbital, and now that s orbital is full. But this hydrogen, when it gets to count its electrons, also gets to count those 2 electrons, so they both get to count those both electrons because they have it some of the time, if not all of the time. So we talk about feeling sometimes in this chapter because it's easier, but it feels as though it has a full electron configuration and that it's like the noble gas helium. So when we form the bonds, atoms achieve a more stable electron configuration and lower in energy so that we can have this be a more stable complex in the end. So that's why they're going to form that bond. This is going to be permanent unless a chemical change occurs. So this is going to remain unless we have some type of chemical change that'll happen. 8 is the magic number that we're going to be looking for everything that's greater than helium. So 8 is the magic number. So octet rule, octet 8. Atoms are going to gain, lose, or share electrons until they have 8 valence electrons. For example, this is sodium, this is chlorine. Sodium is going to lose an electron to become the sodium ion, and this becomes chloride. It gains the electron, so now we have sodium chloride. There are 2 ions with opposite charges. They're going to be attracted to one another. This hydrogen has 1 electron, this hydrogen has 1 electron. Oxygen has 2 lone electrons. They're going to share and pair up those lone electrons in oxygen to form a water molecule. This is covalent. This is ionic. Ionic bonds. So these are formed by a complete transfer of electrons. So we're not sharing them anymore, it's being a complete transfer. What is an ion? An ion is a charged particle. A cation is a positively charged particle. You see a positive ion. An anion is a negatively charged ion. And I like to say a negative ion, anion. So that's how you can remember those two words if you don't know them already. An ionic bond is going to be an attraction, an electrostatically attracted particles, where we have particles that are opposite charges that are attracted to one another. So that's called an electrostatic interaction. So we're going to have that attraction of oppositely charged particles that's going to form. Usually, or generally, these form between a metal and a nonmetal, a metal and a polyatomic anion, a polyatomic cation and a nonmetal, or a polyatomic cation and a polyatomic anion. So those are your options for ionic bonds in general. This is what we would see if we see an ionic bond. So here we have our sodium. And we look in this last little orbital here for sodium, and we see an electron out here. If we look at chlorine, 1, 2, 3, 4, 5, 6, 7, we need to have 8 in that outer shell. So we're going to move this 1 from sodium over to chlorine. So now sodium ion, its outermost shell is empty, and it's a positively charged because it has 1 more proton in the center than it has electrons outside. And now we see that blue electron from sodium has come over to chlorine. Chlorine has accepted that electron in its outer shell, and it has a 1- charge because it has 1 more electron than it has protons in the center in the nucleus. So this would be an ionic bond. This is what's happening. So it's pretty easy to see with sodium and chlorine. Now we have 1 electron transferred. We form sodium ion and chloride, and we have 1 formula unit of sodium chloride. But with something like calcium and phosphorus, calcium donates 2 electrons here. Now calcium is good, it's a calcium ion, but phosphorus is not. It needs another electron, so we see another calcium in solution. The calcium comes along and donates that electron. So now we have, this is good, the calcium ion, and we have phosphide here, but this calcium still has a lone electron. It's going to find another phosphorus in solution to donate that electron to. And now we have, oh, this one's all good and happy. It has the right number of electrons, but this phosphorus still needs 2 electrons. So another calcium comes along and donates 2 electrons to that phosphorus to form another phosphide. And it takes 3 calciums and 2 phosphides in order, well, 2 phosphorus in order to form 1 formula unit of calcium phosphide. So this would have a total charge of 2, 4, 6 plus. 6 plus and 3 minus, and 3 minus would be 6 minus. So overall, this is going to balance each other out. So 1 formula unit of calcium phosphide requires 3 calcium and 2 phosphide. In an ionic bond, we form what's known as a lattice generally. So they are going to be attracted through these oppositely charged electrostatic interactions, and we transfer 1 electron from the sodium to the chlorine, and then we form these ions. And actually you can see in this picture that the cation becomes smaller and the anion becomes larger, and then we form what's known as a lattice. And we can have different types of lattices that form. Now in this one, it's going to be kind of a 1-to-1 where we have a 1 plus and a 1 minus, but with the calcium phosphide, we need 3 calciums and 2 phosphides, so we would see it repeating units. In this here, 1 purple sphere, 1 sodium ion is going to be surrounded, its nearest neighbors are going to be surrounding it, is going to be 6 chloride anions. And each chloride is going to be surrounded by 6 sodium cations. So this is going to be a crystal of this. And there's no molecules. It's repeating formula units through the entire ionic solid. Polyatomic ions. Polyatomic ions are where we have a group of covalently bonded atoms that entirely act together as a group and have a total positive or negative charge on that group of atoms. In this class, unless we see a decomposition, we're not going to see these break apart, so we can kind of keep them together as little units. Now we have ammonium. Ammonium is the only positively charged cation polyatomic ion that we have. We have a whole bunch of our negatively charged ones here, and you're going to become familiar with these. There's a list on there that I'd like you to be really familiar with, otherwise your test is going to take you too long. But as you use these, as you practice, you're going to get to know them. So I want you just identify these as ionic or covalent. So pause it and tell me, is it ionic or is it covalent? Okay, here we go. You paused it, right? Number 1 is ionic because it's a metal and a nonmetal. Number 2 is covalent because it's 2 nonmetals. Number 3 is covalent because it's 2 nonmetals. Number 4 is covalent, they're all nonmetals. Number 5 is ionic because it's a metal and a nonmetal. Number 6 is covalent because it's a metalloid and a nonmetal. Number 7 is covalent, it's 2 nonmetals. And number 8 is ionic because it's a metal and a nonmetal. Well, what about something like this, NH4OH? They're all nonmetals. However, this is 2 polyatomic ions, NH4 plus and OH minus. This is ammonium hydroxide, and it would be ionic. So you do need to be able to recognize those polyatomic ions on this previous sheet. So you need to be able to recognize these, and we're going to be able to use them. And the only way to do that is through practice and practicing with maybe flashcards or something like that. So naming cations that only form one charge is pretty simple. So you just name the element and then add the word ion. So here we have what element? It's magnesium, and then we add the word ion. So pretty simple, but if you don't have this 3-letter word, it's incorrect. Cations take the same name as the element, and if we can form more than one type of charge, if we can form more than one type of cation, you will use Roman numerals. So if you remember Roman numerals, 1, 2, 3, 4, 5, 6 is probably as high as we need to go, but those are your Roman numerals. So what you're going to do is take the element name, put the charge in Roman numerals, and add the word ion. So for example, this is iron. Iron can form iron 3 plus or iron 2 plus. So in this case, it's iron 3 plus. So we need to say iron, parentheses, Roman number 3, and Roman numeral 3, and then the word ion. So iron 3 ion. You must have the word ion when naming cations. It's not necessary for anions, but for me, it's not wrong if you put it for anions, so you might as well just put it down for everything. Anions take the first part of their name from the element. You drop the ending and add "ide." Sometimes that's easier than others. So for chlorine, if we had chlorine, we're going to drop INE, and we're going to add IDE. So chloride. Chlorine becomes chloride. When you go to name polyatomic ions, you're going to name that you have memorized or from the sheet. You do not change it. So I would look this up if I had to, but right now I just already know because you're going to have them memorized as well. That's phosphate. You always need to know that that's phosphate. You got to be able to memorize it, but you recognize it. Now, almost all polyatomic ions end in something other than "ide." For the exceptions are cyanide and hydroxide. Everything else is going to end in something like "ate" or "ite." So that's helpful. Okay, so you need to pause it and try it. If you don't pause it and try it, you're just losing out because otherwise I'm just reading things to you, which is pretty pointless. So pause it and try it. Number 1, potassium ion. Number 2, sulfide. Number 3, copper 2 ion. Number 4, calcium ion. Number 5, nitride. Number 6, nitrate. Number 7, ammonium. Number 8, tin 2 ion. Number 9, silver ion. So silver doesn't need a number here because there's only one possible. Good. All right, moving on. So naming binary ionic compounds. A binary ionic compound is one that's made up of only two elements. So two different elements, but we're going to kind of stretch this and use this for the rest of it, but this is what the way your book went. So first you identify the cation, then you identify the anion. Name the cation, drop the word ion, then name the anion. So here we have aluminum ion and chloride. So aluminum ion, I drop the word ion and put the word chloride. Aluminum ion, drop ion, add the name of the anion, which is cation, which is chloride. So I don't need to put anything about there being a 3 here. So these are what we call charge balanced, which actually makes it a little bit more difficult because you have to remember what the charges of these are, or you have to figure it out. So how do you figure out what the ion is? You can uncrisscross. So if we were to have, we know aluminum is a 3+ ion and chloride is 1-. We can crisscross these charges down and we then get Al1, Cl3. We don't write ones in chemistry, so that would be how we do the crisscross method. You can uncrisscross and go backwards and say that this is a 3 and this is a 1. And you can always use the charges you know to figure out those you don't. So for example, iron bromide. We know that because bromine is in group 7A, it's a 1- anion. If there's 3 times 1-, we have a -3. What plus -3 equals 0 because there's no overall charge on this molecule? +3. So this has to be iron 3 bromide. Why don't you name these? So pause it and try it. Number 1, calcium bromide. Number 2, chromium 3 chloride. Number 3, lead can be 2 or 4, so lead, which one is it? Well, sulfur has 2-, and there's nothing here and here, so this must be 2+, because when we get the smallest, so 2 and 2, we would divide those by 2, and we would get 1 overall, so that's why there's no subscripts there. So it'd be lead 2 sulfide. Barium chloride, iron oxide, but which iron oxide? Uncrisscross, this is a 2- anion for oxygen, so this must be iron 3 oxide. Magnesium sulfide, I don't need a charge there, I don't need Roman numerals because magnesium can only form 1 charge. Lead 4 oxide, copper 1 sulfide, and sodium phosphide. Naming compounds that contain polyatomic ions is actually a little bit easier as long as you know the polyatomic ion names. So we're going to name them in the same fashion, but we're going to first identify the cation, then the anion. You name the cation, you remove the word ion. If it's a polyatomic ion, you just use the name that you have memorized and you don't change it. There's only one polyatomic cation you have to worry about, so ammonium. But then to name the anion, you change the ending to "ide" only if it's not a polyatomic ion. If it's a polyatomic ion, you just use the name that you memorized. So most polyatomic ions are anions, so that's helpful. Here we have ammonium, and we have chlorine, which became chloride, so we have ammonium chloride. Here we have calcium, and we have carbonate, so calcium carbonate. It's actually pretty simple. Let's try it. So pause it and try it. Potassium cyanide. Sodium hydrogen sodium hydrogen carbonate or sodium bicarbonate, both are examples of that. This is called, has 2 different names, so this is also known as bicarbonate, which is what is used for baking soda. All right, magnesium nitrate, ammonium phosphate, lithium fluoride, and rubidium hydroxide. All right, so let's take a look at what's happening with the electrons in these ions. So we follow Hund's rule and the Pauli exclusion principle for atoms. We still follow that. We just have a different number of electrons now. So when we write the electron configuration, it actually helps explain the charges that we memorized for these compounds. You know, group 1 is 1 plus, group 2 is 2 plus, group 3 is 3 plus, group 6, 7, 8, see 5, 6, 7, really don't need to do 8, is 3 minus, 2 minus, and 1 minus, and then these ones don't form ions. So the noble gases, group 8A, they're almost completely unreactive, right? They were the inert gases forever till the 60s. All right, so they have a noble gas configuration. They don't want any more electrons. They're full in their outer shells. The main group elements tend to gain or lose electrons to become isoelectronic. This is a word you need to know. Isoelectronic means it has the same electron configuration as, that's what the word means. And in this case, we're going to talk about stuff being isoelectronic with a noble gas. So this is sodium. We know that sodium forms a 1 plus cation. It does so because it's going to get rid of this 3s1, and then it's going to look like neon. So this is the sodium ion. This is the sodium ion electron configuration, and it looks like neon. So it's isoelectronic with neon. And so it's going to act like a noble gas. This is chlorine. We know chlorine gains another electron to become chloride, right? And so it looks like that. And it does so because it's going to be isoelectronic then with argon. So when it becomes, it gains that other electron, it has the same valence electrons as argon, so it's going to act like a noble gas. So if we recall that the 4s orbital fills before the 3d orbital, remember that? In the first row of our transition metals. Electrons are, when they come away though, when they're lost, are always lost from the highest n values first. So it's not lost in the same order that they're filled. So when I go to form iron 2 plus or iron 3 plus, where do I take those electrons from? And this is going to be important in magnetism. Okay, so when I go to take those electrons from iron, instead of taking them from 3D, I'm actually going to take them from the 4s first. So here I have iron 2 plus, and we don't have any 4s electrons, and I have 3d6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So iron 2 would have 4 unpaired electrons. Here we would have 1, 2, 2, 3, 4, 5, and it would have 5 unpaired electrons in iron 3 plus because it would have that other d electron missing. So it's going to change the magnetism of these elements. Also, it's going to change, and I mentioned this a few slides ago, the size of the radius of the ion. So cations are always smaller than their parent atoms. They often lose a whole energy level. So if you remember with sodium, we got rid of that electron out here. We actually lost that entire energy level, and it should get smaller. And with anions, they're going to be putting more electron-electron repulsions in there, so they're going to be getting larger because what happens is if we talk about magnets, remember size and distance with magnets? The distance from the nucleus is staying the same, but we're increasing the size of this outer magnet, so it's not going to pull as it's not going to constrict as much because the external magnet is larger than, so it can't pull as strong towards the center, if that makes sense. And if it doesn't, don't worry about it. This is just looking at ionic radii. So if you look at the blue, lithium and lithium ion is much smaller than the lithium atom. Sodium atom, sodium ion, potassium atom, potassium ion. You can see they're much smaller, sometimes almost greater than half if you look at lithium and sodium. Rubidium, rubidium ion, and so on. But if you look at the anions here, they're going to be larger. So this is fluorine atom, fluorine ion, fluoride. Chlorine atom, chloride. Bromine atom, bromide, much larger each time we go up because we're adding those electron-electron repulsions in there. So within an isoelectronic series, and what does isoelectronic mean again? We have the same electron configuration, which is easy to tell when something has the same electron configuration because that means it has the same number of electrons, because we always fill in the same order. The size is going to vary. So if I ever ask you to do this, I'm always going to ask you within an isoelectronic series. So here we have an isoelectronic series because oxygen minus 2, so oxide, oxygen had how many electrons? All right, and then it has how many now? So we have to look at the periodic table and tell. Anyway, I'm just going to move on from this, but oxygen had 8 electrons plus 2 because we have 2 minus, it has 10 electrons. Fluorine had 9 electrons plus 1 electron gives us 10 electrons. Neon had 10 electrons and didn't gain any, so it still has 10 electrons. So here, if you just look at this in size, like this is a magnet size 8 and this is a magnet size 10. Now, without thinking too much in depth, if you want to think that this pulls towards the greater magnet, even though we're not really pulling outward, but we kind of are repelling and pushing outward with those electron-electron repulsions, this is going to become larger because the larger magnet's on the outside. Same here, it's not as great, but yes. And here, these are equal, so it's not going to be changing sizes. But radii are going to decrease as the Z, or the number of protons, increase with when it comes to cationic size or anionic size. Now, let's try. I want you to try. So put these in, find the isoelectronic series and put them in order of increasing atomic radius. You need to pause it and you need to do this because it's actually a really simple thing that you're probably going to get wrong on the first couple times you do it, okay? So I want you to be able to get this right on the test because it's really simple. So how many electrons does each one have? Pause it, find out, look on the periodic table. It's a good place to start. So potassium would have 19 electrons, but then it's potassium ion, so now it's 18 electrons. Neon has 10, argon has 18, krypton has 36, phosphorus had 15, plus 3 gives us 18 electrons. Sulfur had 16 electrons, plus 2 gives us 18 electrons. And chloride had 17 electrons plus 1 gives us 18 electrons. So the isoelectronic series is going to be everybody that has 18 electrons. So we can ignore krypton and neon, and then we can put everybody else in order of increasing atomic radius. So if they're the isoelectronic series, you're going to go from the highest positive charge to the highest negative charge here. So it'd be potassium is smaller than argon, which is smaller than chloride, which is smaller than sulfide, which is smaller than phosphide. So there you go. And that's it for this.